Welcome back. So our first goal today is to generate a graph of the relationship y equals sine of x. And before we do this, let's talk a little bit about variable use philosophy. So in the recent past, we had a lot of discussion about the unit circle in the xy coordinate system. We said this radius is 1, and if we have an angle with radian measure t in standard position, then the terminal side of this angle intersects the unit circle at a point with coordinates x and y. And we said this x coordinate, that is by definition cosine of the angle t. And this y coordinate by definition is sine of the angle t. And this was specifically how we defined the functions cosine of t and sine of t. Okay. Another question, this y, is that the same as this y? Is this x the same as this x? And the short answer is it doesn't need to be. Whenever you have a context in which you have variables, the meanings of those variables don't have to extend beyond that context. So in this context right here, t means the angle in radians, x and y mean the coordinates of the intersection point of the terminal side with the unit circle. Okay. But what if I make a brand new coordinate system, x and y, and I say I would like to graph the relationship y equals sine of x. What this means is the x coordinate is going to track this value right here. That is the argument or the input of the sine function. So we understand this represents an angle physically, right? So this x is tracking the angle in the unit circle. And then whatever the output of the sine function is, that's going to get assigned to the y coordinate in this graph. Well, the output of sine of x, or sine of anything, is going to give me the y coordinate in the unit circle. So this y coordinate in this graph corresponds to the y coordinate in the unit circle. Okay, that's kind of nice. Y is still y. Now, if I were to then try to graph this, I could perhaps make a table, right? This is often how we begin to graph things. We say, what if x is 0? So that means I take the value 0, put it in for x. Sine of 0. Well, when the angle is 0, the y coordinate is 0. Okay, cool. What if I do pi over 6? Well, when the angle is pi over 6, the y coordinate is 1/2. When the angle is pi over 4, the y coordinate up here is root 2 over 2, and so on and so on. All right. So if I were to make a graph, then I could say, as I go from left to right on this graph, my angle is increasing counterclockwise. So I'm effectively going around the unit circle. So maybe it's instructive to say, let's mark off 2 pi worth of radians, and this will represent a full cycle around the unit circle, which we're going to start calling a period. Okay, so the highest value y ever achieves is at the top, that is 1, and the lowest value that y ever achieves is -1. And as I go from angle 0 to pi over 2, I'm going to increase my y value. And then as I go from pi over 2 to pi for the angle, my y value is going to decrease down to 0. And then as I go from pi to 3 pi over 2 for the angle, my y value decreases from 0 to -1. And then finally, as I increase my angle from 3 pi over 2 all the way to 2 pi, my y coordinate increases from -1 to 0. So this is my crude sketch of the graph of the relationship y equals sine of x. Now that we've done the crude sketch, let's ask a calculator for a better version. So I'm going to type in here, f1 of x is equal sine of x. Check that I'm in radians. Okay, hit the button. I got that graph. And so we notice certain things. The maximum value up here is 1. The minimum value here is -1. Now, what if we were to go beyond 0 and 2 pi? As in, what if we consider negative angles? So if we go clockwise instead, or what if we go to angles beyond 2 pi? But we understand how coterminal angles work. So really, once I've done one full lap of the unit circle, I just repeat the behavior again. So the graph should repeat itself in behavior every cycle of 2 pi. Let's check this idea. So if I go to menu and I go to window zoom, and I change my window settings such that the x max, so I'm going to go to 4 pi radians. This is 2 laps around the unit circle. Hit the button. See what happened. So this is my first 2 pi radians, and then I repeat the exact same shape of the graph for the next cycle around the unit circle. Let's zoom out even further and say window settings. I'm going to go negative angles now, so I'll say negative 4 times pi. And for the x max, why don't we go crazy? We'll go to 10 pi and see what happens. It's the exact same shape, and it looks squished because I'm sort of zooming in a weird way, but it's the same shape repeated every 2 pi radians. Remember, sine is periodic, and it has period 2 pi, meaning the graph of y equals sine of x is going to repeat its behavior every 2 pi radians. All right, so now that we have a graph of y equals sine of x, this graph, we understand, is going to repeat itself every 2 pi radians. So if we sort of sketch it out like this, we understand that from here to here is 2 pi radians, and from here to here is another 2 pi radians, so that's 4 pi total. We understand that the maximum value here is 1, and the minimum value is negative 1. And in fact, I've been relatively silent on this point up until now, but if you look at the function sine of x, right, and we can call it a function. It has unambiguous outputs. Okay. It has a domain of literally all real numbers, right? Because I can have any positive angle. Just big angles means I'm going around the circle multiple times. Negative angles mean I'm going clockwise around the circle. So the domain is all real numbers, or in interval notation, negative infinity to positive infinity. And the range, the output values, are stuck between negative 1 and positive 1 inclusive. Because in the unit circle, the lowest you can go is negative 1, the highest you can go is positive 1, because you can only go 1 in any direction. Right? So we say the period is how often the graph repeats itself along the x. And I'll put, I guess I won't put x right here, just so we don't have that confusion going on. And then I'll say the amplitude is this special word given to from the middle, how high do you go? And from the middle, how low do you go? This is the amplitude. And keep in mind that the sine graph will always be symmetric in this regard. So from the middle line, you'll always go up by the same amount and down by the same amount. In this case, the amplitude is 1. Well, we spent an entire lecture talking about how to transform graphs. So let's apply those techniques here. So if we say we would like to transform this graph, remember there was this form y equals, and I had an a in front, the function f, and then it was 1 over b x minus c plus d, something like this, right? And we said if I look at the inside part, that's going to transform the x-coordinate. The outside part is going to transform the y-coordinate. And we said something like there is a vertical dilation times a, so that's numbers right there. There's a horizontal dilation of times b, and note the position of b. b is in the denominator. So if this number right here were 7, for example, the horizontal dilation factor would actually be 1/7. And if this were, let's say, 2/5, then the horizontal dilation factor would be 5/2. It's always the reciprocal of the number that shows up in this position. Okay? And then we said there was a translation. The x-coordinate to the right by c, and the y-coordinate up by d. And we said if any of these numbers is negative, negative here means a reflection, a vertical reflection means over the x-axis. If we have a negative here, that's a horizontal reflection over the y-axis. And then if either of these is negative, then it would just mean left instead of right and down instead of up. Okay. So if we take this and we apply it to here, the f function in this case is just sine of x. So we can write this as y equals a times sine of 1 over b parentheses x minus c plus d. Now, different textbooks and different people like to use different letters for these. This is my personal favorite to start with, but I don't actually write this all the time. What ends up happening, and I'm sorry if this is frustrating to you, but this is what we do. We turn this into a capital A, just because A for amplitude, and then sine, and then we put a B in here, and some people put the parentheses, some people don't, and that means totally different things, but I'm going to go with what I've seen in our textbook and do this, okay? So in this context, that means there's a vertical dilation times A. There's a horizontal dilation of times the reciprocal of this value, 1 over b. But then it gets a little bit interesting, because when I go to the translation, notice when I said if you factor out the b versus don't factor out the b, there's a fundamental difference. In order to understand this in the same way that I discussed in a previous lecture, I should actually take this and manipulate it so it looks like the following, right? I factored out a b from that case, because only in this form that looks like that can I understand that the translation is to the right by an amount c over b and up by d. Right? If I just looked at this and said, this is a translation to the right by c units, I would be breaking my priority of doing dilations first and then translations later. So in order to stay consistent, I will always say dilations first, translations second, and you must factor out the dilation factor. That's my stance. And if you want to do things the same way I do, I promise it works every time. So what does this look like in practice? Let's consider an example. Y equals 3 sine of, we'll go with 1/2 x minus pi over 6 plus 1. Now, the first thing I do whenever anyone hands me something of this form is I say, I need to factor out the number in front of x to understand dilations the way I do. So first step, always factor out the coefficient on x. It's 1/2 x minus, and factoring out means I'm going to divide both terms by the number out here. So this divided by 1/2 multiplied by the reciprocal 2 over 1 will simplify to pi over 3. You can verify that 1/2 times x gives you the first term, 1/2 times negative pi over 3 does indeed give you that term. Okay. So in this context, I can understand this as a graph having a vertical dilation with a factor of 3. And the horizontal dilation is going to be the reciprocal of this value right here, so it's going to be times 2. And then we're going to have a translation, so shifts to the right by pi over 3 units, and then up by 1 unit. Okay, so if I try to graph this, I might think to myself, okay, so I have my original graph, and I need to take this and stretch it 3 times vertically, stretch it 2 times horizontally, then shift it to the right pi over 3 and shift it up 1. That's a lot going on at once. So in order to understand this in a slightly easier context, this is what we're going to do. Say original, and then the new. So the original had this thing called an amplitude. And the amplitude was the distance from the middle line up to the top, the distance from the middle line down to the bottom. That was 1. Okay, so the amplitude is 1. But if I take that and I stretch my graph 3 times vertically, then the distance from the middle to the top and the bottom should increase by 3 times. So this new, we're going to say amplitude equals 3. Notice this was a times 2. Right? Or sorry, not times 2, times 3. I really apologize for that. Okay, and then we're going to say the middle line goes up by 1. Because the entire graph is going to shift up by 1, because I do dilations first, then translations, according to this logic. So my middle line used to be 0. Now it's going to move up to positive 1. So we can call this the midline. Used to be at y equals 0. Now the midline is at y equals 1. And this was a plus 1 transition. That's the plus 1 from there. Okay. So I'm going to mark off value 1 and then draw a dotted line. That's going to be my middle line. So I'm going to go up and down from there. How far up and how far down? I'm going to go to an amplitude of 3 up and down. So up to 1 plus 3 is 4. Down to 1 minus 3 is negative 2. So I'm going to have this and this. Now, originally I had a period of 2 pi radians. But if I do a horizontal dilation, then that's going to stretch my period out 2 times. So if I multiply my period by 2, my new period is 4 pi. And then finally, there's this thing called a phase shift. And the phase shift is really the horizontal shift in the context of sine and cosine functions. There's a reason for this. Don't worry about it for now. So in the original, the phase shift is 0 because the original is not shifted at all. But I'm going to translate pi over 3 to the right. So this is a pi over 3. The phase shift is equal pi over 3. So in the near future, we're going to start discussing all of the sine and cosine graphs using this terminology. So our phase shift is pi over 3, and our period is 4 pi. So it's going to be stretched out 4 pi, but shifted over to the right by pi over 3. So why don't I say, okay, I will go to pi over 3 and start my graph, because it's this shape, I'm going to start at the midline. I'm going to start at the midline right there. And then 4 pi in the future, which is going to be this plus 4 pi, means 13 pi over 3. I'm going to return to my midline. That's after I've done one full cycle. Boom. End of one period. So in between, I'm going to hit the middle line halfway in between here. And then halfway between there and there, I'm going to hit the top right there. And halfway between there and there, I'm going to hit the bottom. And then I just sort of connect the dots to the best of my limited ability. Okay? Then, because it's periodic, it's going to repeat itself forever, but we often don't bother drawing more than 1 or 2 periods of this graph. So, returning to this form that our textbook uses, the first thing I always do is I factor out the coefficient on x, so we're looking at something like this. Factoring out b means divide by b, and we understand here that the vertical dilation is by a factor of a, that the horizontal dilation is by a factor of the reciprocal of b, and then we have translation to the right by c over b units, and then up by d. Now, if we think about the way the graph behaves. So first of all, let's manipulate a. So we're going to think very simply, y equals a times sine of x. Okay, so if I take this and I make a new graph that is 2 times sine of x, it multiplies all the vertical values by 2, so I've stretched out. My amplitude has become 2, but my middle line has stayed the same place. Okay. What if I change that to 3? Then it should just stretch me out further, and my amplitude is now 3. 3 from the middle to go down. Okay. What if I change this then to negative 3 sine of x? So that we understand a vertical dilation of a factor negative 3 means you stretch it 3 times, but you reflect it over the x-axis. So it should stay the same sort of vertical height, but then flip upside down. And that's exactly what happens here. Okay, so as a result, we can say that the amplitude of any sine graph is the absolute value of a. How come the absolute value? Because the distance is what we call the amplitude, doesn't depend on the negative sign. The negative sign just tells you the reflection. The distance is just based on the absolute value of the vertical dilation factor. Okay, so then what about the midline? So if we take this vertical shift, then that should shift the graph up or down. We're going to consider a plus 2. Okay, so instead of having a sine of x now, I'm just going to write sine of x plus d. So if I do plus 2, I've shifted the entire graph up by 2, so the middle line now goes through y equals 2. If I change that to a negative 3, then my midline now goes down to y equals negative 3, and that's right through the center of the graph. Okay, so the midline is just y equals d. Then we say, what if we go back to the default and we would like to change the horizontal dilation factor? So if I put a 2 in here, that will be a horizontal dilation of a factor 1/2, so it should shrink all the x coordinates. And in fact, the red graph is squished, and so its period is also squished. So we would say the period of a graph is going to equal its normal 2 pi multiplied by 1 over b. But what if the b is a negative? That just reflects across the y-axis, sorry, but it doesn't change the horizontal distance that you go every time you repeat. So this is going to be the absolute value of b down here. And then finally, the phase shift, if I do minus pi over 6, for example, that just shifts me to the right pi over 6. If I go plus pi over 6, then it shifts me to the left pi over 6. That one is perhaps one of the easier things to understand. The phase shift is just c over b. Okay. So now, what we can do is we can take anything of this form and extract this information from it and then graph accordingly. Let's do a quick example and then end there for today. So what if I say y is equal negative 2 sine of, let's go 1/3, not pi, 1/3 x, and we'll go plus pi over 6. And then we'll go plus 1. Again, actually we did plus 1 last time. Why don't we go plus 3? So we look at this, and the first thing I do is I factor out the 1/3. So we say y equals negative 2 sine of 1/3 factored out x plus. Factoring out 1/3 means divide by 1/3, so you're going to multiply by 3 over 2. Sorry, 3 over 1. That means pi over 2. There we go. Then we can extract amplitude is the absolute value of that a, which is going to be just 2. And then we can say the midline is based on the number that appears in the back right here. That's y equals 3. Then the period is based on the horizontal dilation. I'm going to divide by this number, as in multiply by its reciprocal. So that's going to be regular 2 pi times 3 over 1. That's 6 pi. And then I'm going to have the phase shift is c over b, which is just the number in here except negated. So this is minus pi over 2. Okay, graph time. So first things first, I take my midline and I say, okay, y equals 3. That qualitatively perhaps is right there. And then amplitude is from there how far up and how far down I go. So 3 plus 2 is 5. And then 3 minus 2 is 1. And then I look at my period and my phase shift. Phase shift negative pi over 2 means I have to start my graph pi over 2 to the left. So negative pi over 2. And the sine graph starts at the midline. Then my period is going to be 6 pi. So 6 pi in the future, somewhere all the way out here. If I add 6 pi to this, common denominator, I'm adding 12 pi over 2. So it's going to be 11 pi over 2 all the way out here, where I return to the midline. Then halfway between the beginning and the end, the sine graph hits the midline again. And then halfway between there and there, I will hit either the top or the bottom. Well, normally a sine graph goes up, middle, down, middle. But because of this negative in the vertical dilation factor, reflect over the x-axis, which means instead of going up, I'm going to go down first, and then I'm going to go up later. So my graph will look like this. And it continues forever because it's periodic. Now, the last thing that's worth pointing out today is if I look at one period specifically, right? I said within that period, halfway between the beginning and the end, I hit the midline again. Then halfway between those, I hit either the top or the bottom, and halfway between those, I hit either the top or the bottom. This effectively divides my period into 4 equal horizontal segments. So I will often think of this as the step size, which is period divided by 4. In this case, that would be 6 pi divided by 4 is 3 pi over 2. So what we understand is from the beginning, every time I go to the next interesting point along my sine graph, perhaps I should draw the arrows such that I'm going down here, over here, I'm going to advance by 3 pi over 2 along the x-axis. So negative pi over 2 plus 3 pi over 2 will actually get me the point pi right here, which means my scale is off. Please ignore that. And then if I add pi plus 3 pi over 2, that's going to get me 5 pi over 2. And 5 pi over 2 plus another 3 pi over 2 is going to get me 8 pi over 2, also known as 4 pi. And then 4 pi plus 3 pi over 2 is going to get me 11 pi over 2. And this is how I can find the precise locations of those cool points very quickly. So in conclusion, right, we have this concept. Let me quickly go back and eliminate this. We have the graph of sine of x, and that has this nice default shape. But once we know the default shape of a graph, we can do transformations however we like, shift it around, stretch it, compress it. But in the case of sine graphs, we like to include this vocabulary, and we like to think of it in terms of the amplitude. How far from the middle do you go? How tall is your graph? The midline, where is the middle? How much do you shift it up or down? The period is how long it takes to repeat itself, which is how stretched out you are horizontally. And finally, the phase shift is, are you shifting right or left? And so you noticed that when I did this, I didn't go back and refer to these once I wrote these down, because this gives us a very intuitively nice way to graph transformed sine functions. All right, so we're going to do a lot of practice on this in the problem sets, and next time we'll come back and do the same thing with the cosine graph. Thanks for listening. Take care.